I'm Alan Hayward, and this is about the Dee Bridge collapse of 1847, celebrated its 175th anniversary this year. This bridge was really the only small stain on the brilliant career of Robert Stephenson. It relates to a bridge of 3 spans near Chester, 3 98-foot clear spans using cast iron construction. This slide is taken in the 1850s, but sorry, the 1950s, showing a general arrangement of the bridge as it was after being widened in later years, in the early years of the 20th century for 4 tracks. And you can see Chester in the background. Point about this slide worth emphasising. Notice the bridge is on a slow right-hand curve, and the bridge is also skewed. These are important points. Where did I get my information from? There are a lot of papers written about this bridge in various places. Some of them are not very technical, and the best ones, I think, obviously the source of information is the official report on the accident report by Simmons, Captain Simmons. A further useful reference is the book called Disaster on the Dee by Peter Lewis. I picked up my copy for the princely price of £3.99 near Waterloo Station about 10 years ago. Other faithful companions are Berridge's Girder Bridge. A very valuable paper is that by James Sutherland, The Birth of Pre-Stressing, Iron Bridges for Railways 1830 to 1850. And my treasured copies of the history of the Great Western Railway, inherited from my father. He probably brought this on Paddington Station in the 1930s. And the paper by Paul Sibley, which was a PhD thesis, which has got a lot of extremely useful information. Now, where is the bridge? We're southwest of Chester, and in 1847, Robert Stephenson was constructing his Chester to Holyhead Railway. And the line, of course, was not yet in use, but he had built the Dee Bridge, and trains, for the purposes of constructing the railway to Holyhead, were using the bridge. At the same time, the very youthful Shrewsbury and Chester Railway was being constructed, and construction had reached down to Ruaben, and local trains were beginning to use the bridge during the latter half of 1846. The bridge had been completed in the middle of 1846. So we had a bridge now that was just 6 months old at the time of the collapse. And Henry Robertson, who was the engineer for this Shrewsbury and Chester, was again, didn't have the standing of Robert Stephenson, but again a very competent engineer, famous for such structures as the Chirk Viaduct. What did the bridge look like? Each track of the 2 tracks was carried by 2 girders, 2 cast iron girders, spanned laterally by 10-inch by 10-inch oak joists spanning between, which rested on the bottom flanges of the girders. And there were also some wrought iron ties between the girders to stop them moving apart, hopefully. And 4 inches of timber decking was laid on the top, screwed down into those timbers, and then the chairs for carrying the running rails and check rails were on top. So we had a half-through type of construction, very popular for railway bridges, of course, to give you the maximum headroom beneath, always the challenge for rail engineers. What did these girders look like? Well, they were known as trussed compound girders, which was a system that was developed from the 1830s by engineers seeking longer spans using cast iron, because cast iron, for practical reasons, could only be made and delivered in lengths up to around 40 feet generally. So for longer spans, engineers came up with the notion of joining 2 or 3 together to make a much longer span up to about 100 foot, as in the Dee Bridge. and the girders were joined together using through bolts and also castings over the top to reinforce the joint. And there were further castings at the ends of the girders which were used to anchor the chains or tension rods of wrought iron. So the idea was a combined strength of the wrought iron and the cast iron together would stiffen the bridge, strengthen the bridge. See the detail bottom left there, where the chains change direction through a 3-inch diameter bolt which passes through the girder. The chains were in fact either side of the web of the girder, and the chain was held down by an eye bolt, two eye bolts, to connect with the underside of the girder. And to connect the ends of the flanges, there were wrought iron clips engaging in the ends of the girders. So the whole thing was then strapped together, and by this mechanism, with this vertical bolt, eye bolt, you could change the position of the chain vertically. And so you can see bottom right, the detail there, the hole through the girder webs is in fact oval shaped, giving you 1/2-inch lateral clearance and up to 2.5 inches vertical play for tolerance, and also to enable some form of pre-stress to be applied. And this was the idea: any pre-stress would be applied by pulling down the chain anchorages, in effect pushing the girder upwards, if you like, to relieve it of some of the load. Well, on this date of 24th of May 1847, one of the trains to Ruaben, there were five of these each way, left Chester at 6:15 p.m. To cross the bridge. The train departed some 5 minutes late, and it got to the bridge doing pretty well at 30 miles per hour. I think the driver was obviously trying to make up a bit of time. And he got across the first 2 spans successfully. On the 3rd span, collapse occurred. Now, I've tried to illustrate by this rough sketch of mine what happened. There are no photographs of the bridge before or after, so we rely on witness statements, and the engine driver at the inquest made a full description, which is actually pretty good. And quoting his words at the top, "I felt a sudden sink as he crossed the 3rd span. The engine made a rear up. I gave her all the steam which I had to get across, to pull the train across, hopefully. And in doing this, we plucked the tender away. The tender sunk with the bridge, but we plucked it out. I saw the stoker," that's the fireman, "fall off. He fell on the rails and he was killed instantly. I stopped the engine, but then I went on to Saltney Junction, made motions there that the bridge had fallen, got the engine onto the other line, went back over the bridge, which is on the other track, back to Chester, and gave notice of the accident." A very brave thing for that driver to do, actually. He used the other track, thought nothing of his own safety. So the carriages of the train, there were just 5 very lightweight carriages, about 25 people on the train, and 5 people died, including the fireman. So we see here this engraving that was made. It appeared in the Illustrated London News. 5 persons were killed, and the carriages all ended up in the river. The tender you see on the left there, it has become derailed, but it is fairly intact, and the engine, of course, has gone back to Chester. So what happened? Well, Captain John Simmons for the inspectorate came along, made lots of investigations, and is a very competent report, actually, considering this was before the days of photography, and found 2 fractures, one at mid-span in the cast iron girder, and there was a further fracture towards the left-hand side, towards the abutment at about the quarter span position. So we had 2 failure points. It's possible that the the failure on the left towards the abutment was a consequence of the girder falling, or it might have occurred because of loading on the bridge. That is fairly unclear. There are two versions of the condition of the girder there, made at different times, and they roughly correspond. So at the inquest, Robert Stevenson was called in. He was the overall responsibility for the bridge. He never called in his subordinates. He did it alone. He was apparently extremely shocked by the whole thing. He examined the girder, etc. His view put forward at the inquest was that a derailment of the train had caused the collapse by striking the girders and causing that to happen. He was actually supported in that view by Locke, Vignoles and Gooch, highly renowned engineers, of course. Partially, of course, he was acting for his own employer. You can understand why he went that way. He said that evidence on the tender of the engine, there was paint marks which showed that the tender had struck the bridge, which had just been painted actually, but that was later disproved. That paint turned out to be rubbings off the masonry of the ends of the bridge. And eventually the derailment theory was totally disregarded, was demolished. Henry Robertson, on the other hand, the engineer for the Shrewsbury and Chester, his opinion was the primary break was caused by the locomotive, excessive vibration, the load of ballast which had been added just before the accident, and that the tension rods, this is the wrought iron chain, actually weakened the bridge, putting the top flange into compression. So that was his theory. Now, that was all supported by the Simmons report. Simmons came to similar conclusions to Robertson. The derailment theory was rejected, and the government were now called in. That was suggested by the inquest. The government were called in to investigate the use of iron in bridges, the reason being that there were 60 other bridges of this type around the country, either under construction or had been in use for several years. So it caused a real furore, as much as the 120 years later, the box girder problems in Britain and Australia on steel box girder bridges caused, again, a real furore and caused problems with about 60 bridges. What caused the collapse? Now, the reasons have been put forward in several places. You can read in several papers about theories for it, including derailment, the effect of the additional ballast, which I shall come to, and fatigue, and torsional failure of the girders due to the method of loading them. But the two basic reasons which put forward in James Sutherland's paper, which I've repeated because I think they're absolutely correct. The first one is a basic misconception of truss compound girders, and secondly, B, insufficient torsional and lateral resistance of the bridge. I've then listed some additional factors, straws which broke the camel's back, and we wouldn't be concerned with those if the bridge had been adequately designed in the first place, due to the ballast and various dynamic effects, and also fatigue is another factor. But the basic reasons for the collapse are the misconception of truss compound girders and insufficient torsional resistance. The basic misconception was that it had been assumed that the capacity of the bridge was made up of the addition of the strengths of the cast iron girders in bending and of the chain acting as in a suspension bridge, as though it had been anchored at each end securely to imaginary brick walls at each end, if you like. And that was a misconception. And if you do that, I've done the calculations. On the left-hand side, the capacity of the cast iron girder had been established by Eaton Hodkinson from tests he did before 1830, which is a very simple formula for the braking load depending merely on the depth of the beam, the area of the tension flange, and the depth of the beam. And that's based, if you work it out, on an ultimate tensile strength or breaking strength of cast iron of 6.5 tons per square inch. So you can work out there what the girder would carry, and that's little at the bottom there on the left. W equals 63.6 tons central point load, which is equivalent to a UDL of 1.96 tons, sorry, 1.26 tons per foot UDL. On the right hand side, the chain, regarded as a chain which is anchored securely at each end based on the working stress or the ultimate stress of wrought iron, which is normally taken as 20 tonne a square inch, and the Board of Trade instituted that should be divided by 4 in 1859, giving you a working stress of 5 tonne a square inch. But here, just assuming the load at failure would be at 20 tonne a square inch times the area of the chain. There was a chain each side of the web of the girder totaling 30 square inches. We get 600 tonnes. And if we then work out what that's worth, depending on the span and the rise of the chain, which was approximately 6.5 feet, we get a capacity or a breaking load, sorry, of 2.96 tonnes per foot. The deflections don't come to quite the same, 5.44 for the cast iron inches and 5.24 for the wrought iron chain. So you have to equalise those. You can't get distribution because of the brittle nature of cast iron. So we need to just equalise that to the lower deflection. So we get a combined capacity of the two elements of 4.17 tonnes per foot, whereas the design load is the dead load plus the live load. The dead load I've calculated as 0.45 tonnes per foot approximately. That's the weight of the girders and the timber and so on. The live load, custom and practice on most railways, was 1 tonne per foot run without any allowance for dynamic effects. And we've got 2 girders, so we divide 1 by 2 and we get 0.5. So the total design load is 0.95 tonnes per foot. Divide the failure load by the design load and you get a factor of safety, or factor against failure rather, of 4.3, just over 4. Now that is, factor of 4 was what was declared by Stevenson as what you really required. Simmons, the inspector, required, he said, I expect a factor of at least 3. Now there have been other theories. Fairbairn had done some tests. This is after the defailure, and he came out with a formula there which is very much based on the Hodgkinson little formula, but adds in the effect of the chains. And you can see there there's a factor K which takes account of whether the truss rods are anchored at the end above the top flange or below it. And in this case at D Bridge we're anchored above, of course. And if you go through the calculation, you'll find that the bridge was inadequate according to Fairbairn. The factor against break is 1.42, whereas it should be at least 3 according to Fairbairn. So Fairbairn wasn't very happy, and in the 1849 inquiry into bridges, this all appears, and Fairbairn was pretty unhappy about this method of construction. So what I've done is consider what I think actually should have occurred, if you like. What is the factor of safety on this bridge? And I've split out, as the original designers did, the capacity of the cast iron and the capacity of the wrought iron chain. And the capacity of the cast iron is just its bending strength. And I've worked out a deflection under the dead loads. I get 2.24 inches. If I work out the deflection under the chains, I get a much bigger deflection because the chains are not anchored to a solid wall. They are anchored to the girder itself, well above top flange level. So that induces a bending circular curve downward bending into the girders, which of course is additive to the effect at the top. And it means that in theory the chains carry 35% of the load. The cast iron carries 65, which sounds okay, except remember that the bending moment applied by the chains induces a further sagging moment, which is the sort of coloured bit at the bottom of the diagram of the bending moment there. And the total bending moment, which is the 65% of the load carried by the cast iron, gives a certain figure. You must add on this bending effect due to the pulling in of the chains. So you end up with a total bending moment of 553, whereas if the cast iron did the whole job by itself, you'd get 576. So the only benefit of the chains is about 4%. It's not really worth having, is it? This is a bit of a joke. A guy lying in bed in a very flexible bed gets fed up with it sagging under him, so he decides, oh, I'll truss up the bed with a bit of strong rope tied to the bed heads and strapping underneath the bed. Jumps into bed, same thing happens. Why? It's the basic misconception. You cannot anchor onto the thing you're trying to support. What actually happened? The idea in this bridge was to induce some form of pre-stress in two ways. The first way was construct the 98-foot span on intermediate props to support it, and then jack up to induce an upward pre-camber, if you like. And when the bridge was pre-cambered, attach the chains, make sure they were fully in tension, and then release the props. That was the idea. And the idea was to jack up between 1 inch and 2 inches. That was what was laid down. I believe they only ever jacked up 1 inch. The reason is if you jack up more than 1 inch, the ends lift off at the abutments. I'm pretty sure they would never have anchored the ends down. So they jacked up I think they jacked up 1 inch, released the props, and then you got the full dead load coming in and an effect of the pull of the chains. They then tried to induce further pre-stress by pulling the chains down. And they had, hopefully, still had some play in the vertical hole, the oval hole in the girders to do that by pulling down with the bolts underneath, bolt arrangement underneath the bottom flange. I reckon they wouldn't pull down more than 1.5 inches. You would have to have some sort of tolerance. If you pull down 1.5 inch, you only push the girder up by about 1/2 inch, simply because the cast iron girder is 65% of the strength or the stiffness. The chains only have 35%, so only 1/3 of it. So you don't get much out of that pre-stress, and you can see there the measly effect pulling down the chains has only given a benefit of 13 tons-feet in several hundred. Not really worth having. I've then showed the rest of the history there, placing the ballast, which I'll come to, additional ballast, and then the train itself with its dynamic factor. We end up with the whole stress situation, and at the bottom the effect of lateral loads, which I'll come to. And the stresses at mid-span are all on the right, but I'm going to show those as a summary. James Sutherland in his paper showed this effect very well, illustrates it very simply here. If you try and relieve the girder of load using the chains with the forces upward V, all you do is induce horizontal loads at the anchorages H, which pull it down again. So you end up with no benefit, and the bottom diagram shows you the little bit in the middle of the span, the benefit you get out of it, which is absolutely negligible. So what are the stresses in the girder? This shows the bending stresses at mid-span, and it also shows the factor against break, which of course should be something like 3 or 4. but you can see under dead loads plus ballast, top flange is on 1.9, but as we add the live load down to 1.2, as we add the ballast 1.1, and then with the lateral effects we're down to 1.0, we've actually collapsed. What is the compressive stress based on? It's based on a buckling factor I've used of 0.34, which I'll explain shortly, times the ultimate stress in compression of cast iron of 35. We get a breaking or failure stress of 12 tons square inch. At the bottom flange, I've based the breaking stress on 7.0 ton a square inch, slightly higher than Hodgkinson, and it is the value used by the Railway Engineers Association in the 19th century. Compared with the value by Chetto, Davy and Mitchell tests of 1944 on existing cast iron bridges, which showed quite a range between 6.5 and 8.7 ton a square inch, averaging about 7.9. So my 7 ton a square inch is probably still a little bit conservative. But you can see the factor of safety drops away under full dead load plus live load plus the ballast of 1.4. We haven't quite collapsed, but as soon as we put the lateral effects on, then the stress rises to 7.64 and we've lost the bridge. So the question arises, did the bridge fail in compression at the top flange by some form of buckling failure or by tension at the bottom, which is an interesting question. Now the next factor is insufficient torsional lateral resistance of the bridge. There is no plan resistance on this bridge. There is no plan bracing. The only plan rigidity you've got of any sort is the timber flooring, 4 inches thick, which was screwed down to the cross members, the oak joists, you may remember, which are resting towards the edges of the flanges. Very little calculable lateral resistance. And torsionally, of course, you had the loads, the live loads, certainly resting on one side on the bottom flange. So you have a torsional effect. And the only other restraint was these wrought iron rods at about 8 foot intervals, which were secured, sort of, by this arrangement here of a dovetail joint. And Simmons later recorded you could easily get movement. So this wasn't a secure way of providing any form of torsional or lateral rigidity. Now, what about the buckling resistance? The resistance of a cast iron member with thick webs and flanges largely depends on the St. Venant rigidity, that is the internal shear stress resistance, rather than by warping of the flanges, which is how bridges of U-frame type, you can see on the bottom right, of that type using wrought iron or steel, the capacity of the top flange is really a question of the flange acting as a strut, which is restrained by the U-frame rigidity of the bridge, with the cross girders and planned stability by continuous flooring. None of that was present in this bridge, so the only way it could obtain its torsional resistance is by the internal shear stresses. Thus, the width of the top flange doesn't really come into it too much. And I've got up the factor of 0.34 as a buckling resistance. I adapted BS5400 to try and take I say try because I don't know there's an established theory for this, but using equivalent lateral flanges in warping to represent the torsional rigidity, a bit of a fiddle if you like, but I end up with this factor of 0.34 times the ultimate stress in compression of cast iron and getting about 12 ton a square inch. I've worked out as well the internal shear stresses, which would peak, of course, at the end of the girder as the torsion built up towards the end, and I get a factor of about 1.9. The internal shear stresses due to the torsion plus vertical shear, adding up to about 3.35 tonne a square inch. So it looks as though the girder wouldn't fail in torsion. It's not very clever. I've probably been a bit conservative, taking the eccentricity as 9 inches, because Simmons did show by doing tests on the girders which remained standing on the other track, he got end rotations somewhat less than my predicted figure here of 0.105 radians, or 6 inches out of vertical, which is quite severe, and he got something less than half that, which probably shows that my assumption of the eccentricity of 9 inches is a bit over the top. Now that's dealt with the two main causes, I think, of failure of this bridge, i.e. it was under-designed. There were two straws which I think broke the camel's back. Now, we shouldn't be worried by straws which broke the camel's back if the design had been with plenty of factor of safety, but it didn't have this. And one of the factors, the one, is the ballast. The same day as the collapse, and 1 hour in advance of the train which caused the collapse, ballast was placed on the timber decking. And this had been ordered by Stephenson against the risk of fire damage, because earlier that month a bridge on the Great Western Railway under Brunel had obtained fire damage from cinders dropping from the steam locomotives, and the fire in fact severely damaged and cracked cast iron beams, which all had to be replaced. So Stephenson got concerned. He ordered this ballast to be placed. So it was just before our fatal train, so it must be, I believe, a factor. I've tried to compare the loadings here. At the top you see the train in the position which would have caused the maximum bending moment to mid-span. And you can see as the train approached the quarter span, it produces a bending moment, obviously a little lower, but somewhat higher than if it was a UDL. And this may have caused the second of the two fractures in the girder. That's a bit conjectural. Now, the UDL of the train, equivalent uniformly distributed loading, including impact, which I've allowed 19%, I've allowed some impact due to structural interaction, some rail joint effect, and a bit of lurching from steam locomotives. I get 0.43 tonnes per foot equivalent load, whereas the bridge had been tested when it was tested by before it came into use, and that test loading, they put 3 locomotives end to end on the train, each weighing about, I reckon, up to 36 tonnes, although we don't know the weights of them. I've assumed that 36 tonnes. You had 0.47, so it would appear that the loading due to the train which caused the collapse was less than test loading, which perhaps explains why the bridge hadn't collapsed before. But when you add the ballast, you add another 0.11 tonnes per foot, you get 0.54, which now exceeds the test loading and the freight trains that were using the bridge at slow speed. That all compares with the design loading of 0.5 tonnes per foot. So I think that explains why the ballast is a factor, and was one of the straws that broke the back of the bridge. Now, these are the sort of freight locomotives which may have been used. This is a bit conjectural. I've studied what locomotives were around. These were operated by what would become the London and North Western Railway, and not the Shrewsbury and Chester line. Either the Allen Crew goods engines or the Stephenson long boiler goods engines. These weighed up to 36 tons. So I suspect you could have had 3 of these at the test loading stage. The other straw which broke the camel's back, I believe, is dynamic effects from the locomotive. Now at the top you'll see a photograph of one of the locomotives of the Shrewsbury and Chester Railway, which had only been formed in 1846. They only had 9 locomotives, and 8 of them looked like that one. Now, there's a note in McDermott, Great Western Railway, because this railway was later taken over by the Great Western Railway. These locomotives had a very short wheelbase and were very unsteady. You can see that the wheelbase is actually less than half the length of the locomotive. Now, early steam locomotives had a tendency to yaw, rather like a waddling duck. In other words, a long body and short legs close together. A main reason for that was that there were no, in those days, counterbalancing in the wheels to prevent the oscillating effect of the cylinders hadn't been brought in. There were no counterbalances on the weights. So therefore there's nothing to stop under the action of the cylinders and the pistons operating to prevent this yawing action in plan action. And this would be a worse effect in a locomotive with outside cylinders. And 2 of the Shrewsbury and Chester engines had outside cylinders. And the report of Robertson states that the locomotive which used the bridge at the time of the collapse had outside cylinders. As you can visualize, outside cylinders have a greater lever arm in terms of oscillating effect. Now, it's almost impossible, I would think, to calculate what these forces were due to yawing. I've had a go at it, and I reckon you could get a lateral force of at least 1 ton oscillating in plan. Plus, the bridge is on a curve. There would be another ton also due to centrifugal effects. Funnily enough, locomotive number 5, the one I showed the photograph just now, 19 years later, 18 years later, was involved in a derailment on the same line, on a right-hand curve, double heading a passenger train. The accident was attributed to a permanent way fault. Some gangers were refettling the track and packing ballast under the sleepers, which they hadn't completed before the train appeared. And so there was a bit of a dip in the track, and the front wheels, the front lightly loaded wheel on the locomotive came off the track, went for some distance, and the engine eventually, number 5 is on the left there, turned over, and the other engine pulling the train ended up on the right. And the Board of Trade Inspector, Captain Tyler, noted that the centre of gravity of the engine was behind the middle wheels. So it's a very light loaded front wheel and a very wobbly locomotive. I don't pretend this is anything much directly to do with the D collapse, but it is suggestive of the behaviour of this type of locomotive. So I had a look at dynamic oscillation, because in the Captain Simmons' report on the accident, and he did some testing under moving trains at up to 15 to 25 miles per hour on the other track which hadn't had the collapse. And he records there was a rapid and active vibration going on, so much as to render the edge of the girder beneath my feet quite indistinct, and a considerable oscillation in addition to these movements. So there was a lot of shaking going on. I've worked out the natural frequency of the girders of the bridge, about 2.2 hertz, 2 cycles per second. That's very, very slow as a frequency. Whereas the frequency of yawing, if it coincides with the rotation of the driving wheels, so you get a lateral blow every 15.7 feet, is 2.8 RPS, almost the same frequency. Also, in plan, what is the lateral frequency laterally of this bridge? Very hard to work out. All you've got is girders bowing in plan of 98-foot span and the timber decking. I've had a go at it, but I get something like 2 hertz. These figures are all frighteningly close together. I think it explains the oscillations. And of course, the oscillations would build up. You would have very little structural damping in a structure like this. There was no concrete or anything not much ballast to prevent that. So I think, in effect, the bridge shook itself to pieces. That coincided, of course, with a speed of 30 miles per hour. So again, I've got these stresses shown again, and I think the lateral effect, the 2 red diagrams are the straws which broke the camel's back. You see the final one is the lateral blow. You hit the outside girder with a force of around 2 tons or more. You get a lateral stress of 2.5 ton a square inch, which is almost 50% above what stress you had already from the vertical loading. So you end up failing the bridge. So on that basis, it would seem it was a tension failure. There is at least one witness statement which says that the crack in the girder opened from the bottom. Now that's pretty unreliable. This was by a non-engineer, but it's worth taking note of. So it's still an open question. Did the bridge fail by torsional buckling or tension failure? Could be either, but on balance, I think it's tension failure. Then there's a further factor here, the chain connection at the position where the chain changes direction, where you have this 3-inch bolt. You had 1/2 inch of play. As a train passes from one end of the bridge to the other, the chain clearly clanks backwards and forwards, bangs backwards and forwards in this slot. I'm sure after a few years it would do not much good to the bridge as a whole. Simmons records that when a train came off the bridge there was a clang, and I wonder whether it's these bolts banging against the girder. That's conjectural, but it's suggestive. On the other hand, the change in length of the chains and the cast iron in concert only produces 0.09 relative extension. So that's not enough to connect with the girders and cause composite behaviour, unless at the bottom the bolts had by accident or non-design been arranged like this. Then at the moment of maximum loading you could get composite behaviour between the chain and the cast iron, just in that middle part of the chain, and that has the effect of increasing the section modulus at the bottom by 30 or 40%, which does reduce the effect. This partially explains perhaps why this span collapsed and others didn't. It depends how the thing had been assembled, along with all the other variables of the strength of cast iron and so on, and the way the pre-stressing, so-called, had been arranged. Now, the other factor that's brought up in Lewis's book is fatigue from stress concentration. The cavetto mouldings at the bottom of the flange could have caused perhaps a high stress concentration under the eccentric loading from the cross members. So I've had a look at that. And there's not much information on the fatigue strength of cast iron, except we were involved a few years ago with McDonald in some work on Stevenson's high level bridge, which still has cross girders of cast iron form, and tests were done and came up with this fatigue endurance curve for cast iron, which is this little formula here. And I've applied that by looking at the cross girder. This is a plan cross girder 10 inch by 10 inch timber resting on the edge of near the edge of the flange with 9-inch eccentricity, and the web is here, and working out the stresses and thus an effective width of web which would act in concert with that cross girder. And I've then looked at a sort of stress history as the locomotive crosses any one cross member, a stress history, and worked out during using that fatigue curve what life you would have, and I end up with a life which is a bit conjectural, of course, of about 3 years, which isn't long, but it's more than 6 months. So on balance, I think fatigue failure did not cause the collapse of the bridge, but it soon would have if the bridge had survived for longer. So what happens next? There were more than 60 of these bridges around the country, either under construction or in use, and were under the direction of different engineers, up to 6 of them: Vignoles, McNeil, Stevenson, Hawkshaw, Barlow and Fowler and Gooch. Nearly all well-known, very well-known names. All of these guys must bear some responsibility, you would think. And this is some of the bridges, quite a variety. The Tees Bridge in Newport, 3 spans, continuous. The Tees Bridge, the Lee Bridge, 3 span here, continuous. The bridge at York, 2 span, discontinuous. And the D Bridge, 3 spans, discontinuous. So lots of different possibilities here. But the government were very concerned. They put out a directive. You've got to do something about it. If you have to strengthen or otherwise satisfy the strength of these bridges or replace them. That was the edict that went out, and they asked for a return to be made by all the railway companies to submit a return of all their cast iron bridges. So to find out what was going on. Well, some of the other bridges, this is an early one in East London, which was in fact a covered bridge. It wasn't actually used by locomotives. The wagons were hauled across by rope. This one over the River Lee at Tottenham, this fine painting is owned by Julia Elton, and who kindly sent me the image of it. And you can see here 3 spans, truss-supported centre span, continuous with shorter side spans. What's known as the Scarborough Bridge over the River Ouse in York was 2 spans, discontinuous. And this painting is in the Science Museum. And I've been able to obtain an image through John Addyman, who's a member of the North Eastern Railway Association, the detail of this bridge. Now, it was been declared that this bridge could be continuous. General Pasley, who was a previous inspector of railways, declared that this bridge was continuous. There's no way it is. If you look at the detail on the centre pier, there's no way that there's continuity there, either by the chain or the girder. Definitely simply supported. So why did the other bridges not collapse, the other 59 or so? I've tried to look at this. This is extremely approximate because I haven't got the full details of all the bridges. Other than the sizes of the main girders, I don't know the loading, or in some cases whether the bridges were continuous or simply supported. But 2 of them are continuous, definitely continuous, and I've taken account of that. But you can see the factor against failure of the bottom flange in the D bridge, 1.1. This is just under the vertical loading, assuming 1 tons per foot for live load on all of them, which is possibly not correct for all of the bridges. But you can see the factor is always much higher than 1.1. Just in red are the ones which are a factor of less than 2, which is a factor where you begin to get really worried. But in top flange compression, we're always, sometimes we're up to well over 3, especially here when the bridges are continuous. So on this fairly crude basis, this is why I think D bridge failed. It was because the span was longer and the sizes of the girders were little more than on the other bridges. Aftermath, what happened next? Well, a lot of the bridges were propped, timber props, and bridges were propped and strengthened as well. But we were now moving away from cast iron. After this big scare, cast iron was beginning to take the back seat. Stevenson was going along with his Conway Bridge in 1848. The Commissioner's report on the application of iron railway bridges came out in 1949, and that virtually said, trust compound bridges, they're no good, they must all be removed from the system. Stevenson's Menai Strait Bridge in wrought iron, 1850. Humber's treatise called for live load to be increased from 1 ton a foot to at least 2 ton a foot. That would have caused collapse, of course, quite a few of these bridges. Steel came along in 1877, and in 1883 cast iron was banned for new construction of beams after the Inveraythang collapse in Scotland. The fourth bridge came along in steel, of course, in 1890, and in 1891 a cast iron collapse happened at Norwood Junction, and cast iron girders were banned totally from the railway system. It took a long time. I was still involved in replacing cast iron beam bridges in the early 60s, so it took 70 years to happen. This is one of the bridges that was strengthened, and you can see additional castings were placed, and obviously the effect of this is the girder is much deeper. Also the anchorage is now not above the top flange anymore, it's below it. So this, you've got a much stronger girder. Also the chains are beginning to be a bit more effective. It's an interesting one, the Stockton Tees Bridge of 1844. Stevenson replaced the earlier Stockton Tees Suspension Bridge of 1830, which almost collapsed and deflected alarmingly under train loads. Replaced it in 1844 with truss compound girders, but after the decollapse, propped with timbers. Those timbers remained there until the bridge was eventually replaced in 1907. So those timber props lasted 60 years, which is pretty good. And the interesting thing to see on this bridge that it was continuous. The chains are continuous over the intermediate piers, which of course vastly improved the strength, the continuity, and the fact that chains were continuous. And you can see here the chains interconnecting over the pier, and at the end there's a short side span which is continuous with the next span. So this continuity enormously increased the strength. It meant that this bridge could well have survived somewhat longer, but anyway, it was propped and eventually replaced. And after replacement, and I took this photograph only in the last couple of years, you can see where the props were placed in these iron shoes, cast iron shoes into the piers. The props would have been here. The bridge of course got reconstructed with lattice girders, and that's been replaced by newer steel girders in the last 10 years or so. Another of those bridges, you can see the sign of timber props originally there. This bridge was a wrought iron replacement of 1881. The bridge is now disused anyway. Now there is a surviving relic at Halifax. This construction here is part of a truss girder bridge, which originally wasn't at this location. It's really being used as a parapet. and it's obviously come from another site, and it's a matter of conjecture where it came from. It had been thought that it was coming for a bridge over the Nottingley Canal on the Lancashire and Yorkshire system. Ron Fitzgerald, who kindly provided this sketch which he made, he did a survey of those girders surviving at Halifax, a very detailed survey. You can learn quite a bit from that, the way the chains were obviously anchored here and the intermediate splice position here. And it conjecturally, did it come from that bridge across the Nottingley and Goole Canal, which has an appropriate span which seems to fit with that Halifax remain. However, this bridge has been identified by this drawing, which appears in Humber's book of 1857, as published by the designer, and it's showing a rather different arrangement with girders which are rather deeper and a different arrangement at the end. So it's a bit of a mystery. Did the relic come from some other place? And that's a little mystery still to solve. But the Commissioner's report into the application of iron into railway structures came out in 1849. It now said, very conservative, in a cast iron bridge, the breaking weight should not be less than 3 times the permanent load, added to 6 times the greatest moving or live load. So they really went over the top, very understandably. And this is now the beginning of the end of cast iron girders. And of course we're into the age of wrought iron. And this bridge, the Torksey Bridge, was 2-span continuous of 1849. Interestingly, the opening was delayed by our friend Captain Simmons, who was involved at the D Bridge, because he didn't like the continuity arrangement. And there was some months' delay until the bridge was opened. Here's a contemporary bridge just a few miles away at Gainsborough. 2-span continuous, same span as Torksey Bridge. That eventually developed fatigue cracks, but only after 140 years, so it did very well. And we were involved with replacing the superstructure in steel 2-span continuous. There's still quite a bit of cast iron around, not in girders carrying rails, but in edge girders. There are quite a few examples like this, edge girders carrying just parapets, whereas the inner girders will have been replaced by wrought iron or steel over the years. The Glynde Reach Bridge, trestle piers due to Rastrick of 1846, and the 2 bridges at Chepstow, the Y Road Bridge arch construction and the Brunel's Rail Bridge cast iron columns, cylinders, but of course the superstructure long since replaced. Where is the D Bridge today? It was widened to 4 tracks in the early 1900s on the outside here. So these are the new tracks, and the old bridge would have been here. So the girder which failed would have been just there. And eventually those 2 tracks have become disused, and the bridge was extensively refurbished, the 2 tracks which remain, in 2012. Notice again the plan curvature and the skew, which are all factors. We mustn't forget Robert Stevenson. He took full responsibility for the errors which occurred. But look at his achievements during that period, mammoth achievements in the 1830s and 40s, not only in bridges, but of course in locomotives and in tunnelling. Can we learn anything out of this lot 175 years later? I think we can. Novel structures, which D was. When we have novel structures, I think we should do more in the way of in-principle verification. This failure was in Florida about 5 years ago. There have been reams and reams written about why this bridge failed, which failed when these temporary supports were removed, transporters removed, and the bridge landed here, that this highly inclined strut member failed by punching its way through the end of the bridge. It's just punching for shear. It's a basic failure. It doesn't need reams and reams of highfalutin analysis. There was apparently a finite element analysis by the designer, but he didn't pick up the obvious failure. Stability and strength, something I think we should check using in-principle verification, simplified methods. I call it WL/8 technology. I've recently become aware of a structure being due to be reconstructed for a different purpose, where the lack of plan, stability and stabilization of a top chord of a truss has been ignored by a famous firm of designers. It's essential we look at these basic things. Resistance to horizontal effects, that's pretty well taken care of in modern bridges. And for example, with railway loading, we have the nosing force, which is a nominal 10 tons, very useful to have. It is only nominal. It was not introduced though until 1944, and it's now ended up into Eurocodes. It's a nominal force, but it's useful to have such a thing. And then advanced analysis. Okay, we can fool ourselves, we can design structures, novel structures very cleverly with advanced analysis, but there is still scope, I think, for doing in-principle verification. And I think that should be done after the advanced analysis as well as before. I'll quote finally by William Fairbairn in 1849. He said, "In many of our operations, we are the children of habit." Finally, acknowledgements. These people have made a contribution very much in pointing me in the right direction. Anyone who's got queries, there are my contact details, please email me. Thank you.